Welcome to this quick explainer. I'm really glad you could join us today. So, we're going to rapidly clear up the confusion around some of the absolute most overused buzzwords in tech right now: artificial intelligence, machine learning, and deep learning. We're going to break down exactly how they differ, how they connect, and the massive kind of hidden challenge that's threatening their future. And we're going to do the whole shebang in under 5 minutes. All right, let's dive right in. Okay, first off, let's tackle what is probably the biggest misconception in tech today. Does all artificial intelligence actually learn? Well, the reality might actually surprise you because the answer is a resounding no. Not all AI learns. To figure out why that is, we really need to look at how these technologies are categorized. Let's start with decoding the AI buzzwords and separating the reality from the hype. So, starting right at the top, artificial intelligence is basically the broad, overarching grandparent of the whole tech family. It just refers to any system designed to mimic human reasoning or decision-making. Now, as you probably know, early versions of AI, they didn't learn a single thing. They just followed strict, hard-coded if-then rules. Think about an automated loan approval system, right? Like, if the credit score is over 750, then approve the loan. It totally acts intelligently, but it's really just following a rigid script. Now, if you look at how it all fits together, it's really helpful to think of these not as competitors fighting it out, but more like a giant Russian doll of nested technologies. Every deep learning system is a subset of machine learning, and every machine learning system is a subset of AI. But as you zoom in on those inner layers, the systems gain a lot more autonomy and, honestly, require way more data. I absolutely love this analogy from our sources. It says, AI is the objective, machine learning is the strategy, and deep learning is a high-capacity implementation of that strategy. That just perfectly nails how these three concepts work together. They're not separate things. They are a unified continuum moving toward greater and greater complexity. Which brings us to machine learning, the strategy, moving from rules to data. To get a handle on this, let's take a really quick sweep through history. Back in the 1950s, symbolic AI was king, and it relied heavily on those explicit logic rules we just talked about. But then, in the 1980s, machine learning rapidly accelerated, basically because data suddenly became wildly abundant. Fast forward to the 2010s, and the massive availability of specialized hardware ushered in the deep learning era, which allowed for these incredibly complex, multi-layered neural networks. So, the absolute game changer here is that pivot from rules to data. In traditional symbolic AI, you and I, the humans, had to input both the data and the explicit rules just to get an answer. But machine learning flipped the script. It acts more like a really talented apprentice. We feed it the raw data and the answers, and the machine actually figures out the rules on its own. It learns the patterns without us having to sit there and hand code every single step. And that leads into deep learning, the powerhouse, really the prodigy child of AI. When you compare them side by side, it's pretty clear why businesses have to be careful about which one they choose. Machine learning is efficient, it's transparent, and it absolutely loves structured data, like your standard spreadsheets. It runs perfectly fine on regular CPUs and is highly interpretable, meaning we can actually understand why it made a specific decision. Deep learning, on the other hand, craves unstructured data. We're talking raw images, text, video. It demands massive computing power from specialized hardware, like GPUs, which unfortunately creates a sort of black box where interpretability is super low. So, to sum that up, deep learning is incredibly powerful and highly independent. It can discover really complex features automatically by pushing information through deeply layered neural networks. And for things like facial recognition or translating languages, the accuracy is literally unmatched. But there is a catch. You sacrifice transparency, that black box problem, and it has a completely voracious appetite for computing power. Which brings us to our final hurdle, the computational brick wall, the hidden cost of deep learning. That voracious appetite I just mentioned, well, it forces a pretty abrupt pivot in our narrative. The computing power demanded by deep learning isn't just growing steadily, it is scaling quadratically. It is shooting straight up. While our hardware performance is definitely improving at a steady pace, deep learning's demands are just exploding exponentially. We are, quite literally, outpacing the physical capabilities of our hardware. Basically, we're hitting a hard wall. The incredible flexibility of these deep learning models relies on something called over-parameterization, which means we have to massively scale up the training data. But with the growth in computing power per chip actually slowing down, our current strategy of just throwing more servers and more energy at the problem, it's economically and environmentally unsustainable. We simply can't power our way through this anymore. A fundamental re-architecting of these models is urgently, desperately needed. Which leaves us with one final, pretty provocative thought. If the prodigy child of AI is running headfirst into a computational brick wall, what happens next? When we simply run out of computing power, how are we going to break through the limits of tomorrow to keep AI advancing? It is a huge question, and honestly, every researcher and tech leader is racing to answer it right now. Well, thank you so much for joining me for this explainer. I really hope it gives you a completely new lens to view the daily headlines through. Keep questioning and keep learning.